So this is a short tutorial on atomic structure. So under this chapter, you need to know the subatomic particles, protons, neutrons, and electrons, and how they behave in an electric field. As well, you need to memorize their mass and charges, and you need to know the respective shapes of the SPDF orbitals and how to determine the electronic configuration of elements in a periodic table. The last part you need to know is the factors which affects the ionization energies of elements, which is the screening or shielding effect and the nuclear charge. Okay, so the first thing that you need to know will be the subatomic particles, protons, neutrons, and electrons. So the respective positions in an atom, protons and neutrons are found in the nucleus, and electrons are found around the nucleus. So the relative masses is 1, 1, and 1 over 1840. The respective charges will be positive, neutral, and negative. And how they behave in an electronic field is that the protons, as they are positively charged, they will be attracted towards the negatively charged plate, and the neutrons, as they are neutral, they will just move across horizontally and not get attracted by any of the plates. And the electrons, being negatively charged, they will be attracted towards the positively charged plate. Okay, and how do we calculate the angle of deflection in an electric field is the charges over their mass. So the mass will be given in the question, or you can calculate it using the respective masses, and the charges you can use the relative charges to calculate it as well. So now we need to know that in an electric field, the electrons will be deflected to a greater extent than the protons because the electrons have a smaller mass, and that the greater the charges of the particle, the greater will be the attractive forces exerted on it, and the angle of deflection will be greater and is definitely calculated based on the angle of deflection formula. And if there are two particles moving with the same speed, the heavier particle will possess a greater energy because more energy have to be exerted on it to cause it to deflect. So the heavier particle will be deflected to a lesser extent because it's heavier, so it's harder to move. Okay, so now we learn the four quantum. The representation is very easy. It's just atomic number and the mass number. And sometimes periodic table flip it the other way around. So you need to actually look closely at the bottom of periodic table. They'll tell you the relative position, so don't confuse yourself. And the four quantum numbers is principal quantum number, orbital quantum number, magnetic quantum number, and spin quantum number. But as these three are not in syllabus, so today we'll only be learning about the principal quantum number, which is in the A-level syllabus. Then under the principal quantum shell, there will be subshells, SPDF, and under each subshell, they will have orbitals, and we can calculate the number of electrons in the subshells. So for the S subshell, it will hold 2 electrons, P holds 6 electrons, D holds 10 electrons, and F holds 14 electrons, and so on. And there will be like other subshells like G and other alphabets which is not in the A-level syllabus. So the number of orbitals there are will be basically calculated using the principal quantum number. So example, in the first, if the principal quantum number is 1, the total number of orbitals will be 1. But if the principal quantum number is 2, then the total number of orbitals will be 4. And it's calculated like that. That means that because in principal quantum number shell 1, 1s orbital will be found, and principal quantum number shell 2, 1s, 2s, 2p orbitals will be found, and all of them add together will be a total number of 4 orbitals. So therefore it's calculated using this formula. So what is an orbital? An orbital is basically just a 3-dimensional volume of space around the nucleus in which there's a high probability of finding an electron. And this is the sequence in which the electrons are being filled up in an electron shell. So basically it's just to draw like that, the arrows, and so on and so forth. So for this part is very important because for electronic configuration involving more than 18 electrons, 4s orbital is filled before 3d orbitals. Before the 3d orbitals, it will just follow according to this sequence: 1s, 2s, 2p, 3s. However, because the energy at the 3d, there will be a change in energy. So because there's an irregular decrease in energy, the proximity to the nucleus, the energy of s orbitals will be lower than the d orbitals. So the 4s orbital is filled before the 3d orbital. So in this case, when the electrons are filled up, when electrons are filling up electron shells, the s orbital will have a lower energy than the 3d orbital. Take note of this. However, when you form ions from atoms, the electrons are first removed from the orbitals with the highest energy. In this case, it will be the reverse order. That means now the 4s orbital will have a higher energy than the 3d orbital. The reason why is because before they are filled, the 4s orbital and the 3d orbital don't have any electrons. So when the part is during the process of filling, so the 4s orbital, there's nothing shielding the 4s orbital electrons. So therefore it will have lower energy and thus it will be filled first. But after it is filled, the 4s orbital will be shielded by the fully filled 3d subshell. So therefore the energy now will be higher than the 3d subshell, and therefore it will be removed first. And there are anomalous electronic configuration and other exceptions that you need to take note. Is the chromium, which is 3dF, 3d5 4s1, and the copper, which is 3d10 4s1 instead of 3d9 4s2, and this one instead of 3d4 4s2. The reason why is because electrons prefer to be half filled instead of partially filled, and fully filled instead of half filled. So if they get a chance, they have the chance, they will prefer to be singly filled before pairing up. So therefore, resulting in these two exceptions. But of course there are other exceptions, but we won't learn it in the A-level syllabus. Okay, so now for the orbitals, SPDF, they will have this shape. The s orbital will have a spherical shape, and the x, y, z of the p orbitals will have a dumbbell shaped, and d orbital will have 2 dumbbell shape, which is shaped like a clover, and the respective axis is very easy. Is d, if it's dxy, it will just, the dumbbell will just be in between the x and the y axis. Like in this case, the y is here and the x is here, so it will be here and here. It will be found in between. Then the z orbital is an exception because here got another donut. This one is the z square orbital, so you need to take note of this. This is basically a table that I've made to make the differences more clear. But since I explained it to you just now, so it's a bit redundant. So now the sequence of filling of electrons, the off-ball principle. The electrons occupy the orbitals with the lowest energy first, like I said in the case of the 3d orbital and the 4s orbital. So and when they have lowest energy, the atom is in the ground state, so it will fill the orbitals with occupy orbitals with lower energy before they occupy orbitals with higher energy levels. Because electrons closer to the nucleus are more strongly attracted, so it'll be easier for the electrons. The Pauli exclusion principle in this case is two electrons occupying the same orbital. They have opposite spins and is basically represented this way. You draw it using squares. So they are singly filled first before pairing up. So this is called opposite spins. Yeah, opposite spins. So the Hund's rule is basically electrons occupy orbitals singly with parallel spins before pairing can occur, as I've said earlier. Electrons avoid being in the same orbital because they want to minimize the inter-electronic repulsion between the electrons. Okay, so now the last point is the ionization energy, which is affected by the number of electron shells and the effective nuclear charge. Okay, the number of electron shells is because as you go down the group, the number of electron shells increases. So this increases the atomic radius. The valence electrons are now further away from the nucleus, and the attractive forces between the positively charged nucleus and the negatively charged electrons will decrease. Less energy is required to remove the valence electron, and hence the ionization energy will decrease. The effective nuclear charge is basically affected by the nuclear charge and the shielding screening effect. It's basically calculated by the attractive forces, which is the nuclear charge, and the repulsive force, which is the screening effect between the nucleus and the electrons. So the nuclear charge is basically affected by the number of protons in an atom. As the number of protons increases, the nuclear charge increases. So the attraction of positively charged nucleus for the negatively charged electrons increases. More energy is required to remove the valence electrons, and total ionization energy increases because it's harder to remove the electrons. The shielding effect, because electrons in the inner quantum shells, they actually cancel out the attraction between the valence electron and the nucleus because they are found in between. It's like they are sandwiched in between. In this case, if this is the nucleus, this one is the valence shell, then the inner quantum shells will be here, the electrons will be here, so it will cancel out. This one is positive, then this one valence electrons will be negative, so it cancels out because it's found in between. It will shield it. Okay, so as there's an increase in number of inner electron shells, the shielding screening effect will increase. So therefore, it will be easier for you to remove the electrons. Yeah. So all these are just notes. It's very lengthy, so I just cut it short. Okay. And some exceptions in the general trend is that between group 2s and 3s, there will be another p orbital, which is the 2p orbital. Example, in this case, we use beryllium and boron. So the 2p orbital is further away from the nucleus, is at a higher energy level than the 2s, so it's less strongly attracted to the nucleus. So less energy is required to remove the 2p electron, and therefore lower first ionization energy. And between 5 and 6, group 6, electrons prefer to be singly filled first. So in this case, they'll have singly filled 2p orbitals. This one will have 2 singly filled 2p orbitals and 1 fully filled orbital. So the paired 2p orbital experience inter-electronic repulsion. Less energy is required to remove the electron, and they will have lower first ionization energy. Okay, so that is it for atomic structure for the A-level syllabus. Thank you.